Mars, the fourth planet from our Sun, has captivated humanity for centuries. Its reddish hue has earned it the moniker Red Planet. Our fascination with Mars grows with its potential to harbor life. The allure of Mars lies in its proximity and potential to answer questions about life beyond Earth. Join us as we uncover the secrets of our enigmatic neighbor. Mars is significantly smaller than Earth, with a diameter roughly half that of our planet. This smaller size translates to a lower surface gravity, approximately 38% of Earth's. The surface of Mars is a diverse landscape, featuring towering volcanoes, deep canyons, and vast plains. Olympus Mons, the largest volcano in our solar system, dominates the Martian landscape, reaching heights 3 times that of Mount Everest. Valles Marineris, a system of canyons stretching over 4,000 kilometers, dwarfs Earth's Grand Canyon. The Martian crust is primarily composed of basalt, similar to volcanic rock found on Earth. However, evidence suggests that the Martian mantle may contain a higher proportion of silicon than Earth's mantle. The Martian core, believed to be primarily iron and nickel, is likely smaller and less dense than Earth's core. Unlike Earth's active magnetic field, Mars possesses only a weak, localized magnetic field. This lack of a global magnetic field leaves the Martian surface exposed to harmful solar radiation, a significant challenge for future human exploration and settlement. Mars has a thin atmosphere, mostly carbon dioxide, with traces of nitrogen, argon, and oxygen. The pressure is less than 1% of Earth's, preventing liquid water. Temperatures vary from 20 degrees Celsius at the equator to minus 153 degrees at the poles. Dust storms can engulf the planet, affecting visibility and communication. Fine dust challenges robotic equipment and potential habitats. Over billions of years, Mars transformed from a wetter environment to the cold, dry desert we see today. The exploration of Mars began centuries ago with telescopic observations by astronomers like Tycho Brahe and Johannes Kepler. These early observations helped determine Mars's orbit and position within our solar system. The first attempts to send spacecraft to Mars began in the 1960s. The Soviet Union launched several missions, but most were unsuccessful. In 1965, NASA's Mariner 4 became the first spacecraft to successfully fly by Mars, capturing the first close-up images of the planet's surface. These images revealed a cratered, desolate landscape, shattering the hopes of finding advanced Martian civilizations. The subsequent Mariner missions provided further insights into the Martian environment, including evidence of ancient riverbeds and the presence of water ice in the polar caps. These discoveries fueled speculation about the possibility of past life on Mars and laid the groundwork for future missions designed to search for evidence of biological activity. NASA's Mars exploration program has been a cornerstone of our understanding of the Red Planet. From the early Mariner flybys to the sophisticated rovers currently exploring the surface, NASA missions have revolutionized our knowledge of Mars's geology, atmosphere, and potential for life. The Viking missions in the 1970s were a landmark achievement, landing the first spacecraft on the Martian surface and conducting experiments designed to detect signs of life. While the results of these experiments were inconclusive, they provided valuable data about the Martian soil and atmosphere. The Pathfinder mission in 1997 marked a new era in Mars exploration, deploying the first rover, Sojourner, to traverse the Martian surface. Sojourner, a small, 6-wheeled robot, demonstrated the feasibility of using rovers to explore the planet's diverse terrain. The Mars Reconnaissance Orbiter, launched in 2005, has been instrumental in mapping the Martian surface in high resolution, providing detailed images of geological features and potential landing sites for future missions. The orbiter's instruments have also detected evidence of subsurface water ice, further fueling the search for past or present life. The Indian Space Research Organization, or ISRO, achieved a remarkable feat with the Mars Orbiter mission, also known as Mangalyaan. Launched in 2013, Mangalyaan became India's first interplanetary mission and demonstrated the country's growing capabilities in space exploration. Mangalyaan entered Mars orbit in 2014, making India the fourth space agency to successfully reach Mars. The mission was notable for its cost-effectiveness, demonstrating that ambitious interplanetary missions could be accomplished with limited budgets. The orbiter carried 5 scientific instruments to study the Martian atmosphere, including a methane sensor to search for traces of this gas, which could indicate biological activity. Mangalyaan also captured stunning images of the Martian surface, providing valuable data for scientists studying the planet's geology and climate. Mangalyaan's success marked a significant milestone for India's space program and demonstrated the country's growing prominence in the field of space exploration. The mission's cost-effectiveness and scientific achievements paved the way for future Indian interplanetary missions and inspired other nations to pursue their own Mars exploration programs. The search for water on Mars has been a central theme in Mars exploration. Water is essential for life as we know it, and its presence on Mars would significantly increase the chances of finding past or present life. Evidence from past missions suggests that Mars was once a warmer, wetter planet, with flowing rivers and possibly even oceans. The discovery of recurring slope lineae, or RSL, on Martian slopes provided tantalizing clues about the presence of liquid water on the planet. These dark streaks, which appear and disappear seasonally, are believed to be caused by the flow of briny water. Radar data from orbiting spacecraft has revealed the presence of vast subsurface ice deposits, particularly in the polar regions. These ice deposits could represent a significant reservoir of water that could be utilized by future human missions. Understanding the distribution and accessibility of water ice is crucial for planning long-duration missions and potential settlements. Terraforming Mars. The process of transforming the planet's environment to make it more Earth-like is a long-term goal for some scientists and engineers. This ambitious project would involve altering the Martian atmosphere, increasing its temperature, and introducing liquid water to the surface. One proposed method for terraforming Mars involves releasing greenhouse gases into the atmosphere to trap heat and warm the planet. Increasing the atmospheric pressure would also be necessary to allow liquid water to exist on the surface. Introducing microbial life to Mars could play a role in transforming the planet's environment. Certain types of microbes could convert carbon dioxide in the atmosphere into oxygen, making the air breathable for humans. Creating a magnetic field around Mars would be crucial for protecting the planet's atmosphere from being stripped away by solar wind. Developing the technology for such a project would be a monumental undertaking. Terraforming Mars presents numerous technological and ethical challenges. The sheer scale of the project would require vast resources and international cooperation. Developing the necessary technologies, such as large-scale atmospheric modification and magnetic field generation, would require significant advancements in engineering and space travel. Introducing terrestrial life to Mars could potentially contaminate any existing Martian life, preventing us from discovering and understanding it. The decision to alter another planet's environment raises fundamental questions about our role as stewards of the solar system. The potential for conflict over resources and territorial claims on a terraformed Mars must also be addressed. International agreements and regulations would be necessary to ensure equitable access to resources and to prevent conflicts between nations or private entities. Establishing a governance structure for a Martian colony would be a complex undertaking. The exploration of Mars represents a profound chapter in human history. From ancient observations to modern-day robotic missions, our fascination with the red planet has driven us to push the boundaries of scientific discovery and technological innovation. The quest to understand Mars's past, its potential for harboring life, and its prospects for future human habitation has captivated scientists and the public alike. The journey to Mars is not without its challenges. The vast distances, the harsh environment, and the technological complexities of interplanetary travel present formidable obstacles. However, the potential rewards of establishing a human presence on another planet are immense. Mars could serve as a backup location for humanity, a stepping stone for further exploration of our solar system, and a source of invaluable scientific knowledge. The Martian frontier beckons, offering a new chapter in human history and a chance to expand our reach beyond Earth.